Hello. So I'll be speaking about efficient quantum algorithms for some instances of the multiple hidden shift problem. And this is joint work with Gábor Iványos and Miklós Santa. And I'll begin by defining what the hidden shift and the hidden multiple shift problems are. So let's begin with the hidden shift problem. So throughout this talk, Q will be a prime number. And so let Q be prime and S be a sufficiently large finite set. So the hidden shift problem is the following. So let F be a function from ZQn, n tuples to S. So F is an injective function and G is a shifted variant of F. So Gx is equal to Fx minus S. So the hidden shift problem is to determine S given oracle access to F and G. And now let me define the multiple hidden shift problem. So for the multiple hidden shift problem, we are given more shifted copies of F. So let H be a subset of ZQ. So it is a finite set of size bigger than 2. And let's define the shifted function Fs, which is now from ZQn direct product H to S. And Fs of UH is F of U minus HS. So the multiple hidden shift problem is when you have more copies of the shifted function. So HMS Q and R is defined for R between 2 and Q minus 1. And the problem is to recover S given oracle access to this multiple copies of to the oracle Fs. So now let me motivate this problem and say why it is interesting to study it. So let's see what it looks like to solve this problem in the quantum form. So the natural thing to do would be to set up a superposition over all the over ZQn with all the shifted indices as well. So we set up a superposition of A0 and B1, and then we compute this, and then we invoke this oracle and make a measurement. So for the hidden shift problem, it gives us states of the form 1 by square root 2 A0 plus A plus S1, where A is sampled uniformly at random from ZQn. And for the hidden multiple shift problem, one would get quantum states of the form 1 by square root R, A0, A plus S1, A plus 2S2, A plus R minus 1, S, R minus 1. And so the task would be to recover the hidden shift given sufficiently many copies of such states. So one of the main motivations for studying such problems is that it has been known from 2004 that classical lattice problems reduce to noisy variants of these hidden of the hidden shift problem with the two shifts. So by noisy I mean that we don't have a perfect oracle, but with high probability one gets states of this form, and with some small probability one gets a completely arbitrary state. So the implication is that if one had a polynomial time algorithm for the hidden shift problem, one would also be able to solve the lattice problem. So one expects these hidden shift problems to be really hard. So the same is true for the hidden multiple shift problem. So Regev's argument actually can be extended to show that there would be a polynomial time algorithm, that if we had a polynomial time algorithm for HMS Q and R for certain parameters. So Q should be large and R should be much smaller than N. So it should be close to the 2 case rather than the Q case. So it's folklore. It's known to the people who work in this area, but it's not. But no algorithms have been found in this line. So it's important to understand which cases of HMS are easy and which ones are hard. So what's the boundary of tractability for these problems? So one immediate observation is that if R is equal to Q and we have access to all the possible shifts, then this problem is easy. It is the abelian hidden subgroup problem, and it has an efficient algorithm. So the hidden multiple shift problem interpolates between the easy hidden subgroup problem when you have all the shifted copies of the function when R is equal to Q, and the hard hidden shift problem when R is equal to 2. And the motivation is to study what happens for the intermediate cases. So here the main result we prove is the following. So the main theorem for this talk is that for prime Q, there is a quantum algorithm for the hidden multiple shift problem, HMS Q and R, with time and sample complexity n plus Q, Q minus R squared. So this is giving a polynomial time algorithm when Q minus R is a constant, and Q can be arbitrarily large. Like Q could be, so Q can be large, but Q minus R should be a constant. So it's still close to the hidden subgroup case rather than the hidden shift case. But I'll indicate how this extends previous results and why this is interesting. So the hidden shift and the multiple shift problems are related to classical linear algebra problems over finite fields. So of course, the most well-known and well-studied hard problems based on noisy linear equations over finite fields are the learning parity with noise and the learning with errors. So these have been very well studied in cryptography, and one can do all kinds of things if these things are hard for quantum computers. So the hidden shift and the hidden multiple shift problems are related not to LPN and LWE, but to slightly different problems based on linear equations over finite fields. So these problems. So for these problems, we have partial information about the linear equations. So let me start with what was known about the hidden shift problem. So it was known to reduce to the learning with disequations problem by Friedel et al. In 2004. So what's learning with disequations problem? So there is a linear function. So this notation will also be used for the rest of the talk. So let's say that this capital L denotes a linear function from ZQN to ZQ. So the learning from disequations is to recover L up to a constant, given random samples such that LU is not equal to 0. So you're given linear equations, and in each equation, you know that it can assume Q minus 1 possible values. Like it could take any values except 0. And if you're able to learn the linear function from such samples, then you also would be able to solve the hidden shift problem. So that's the implication here. So in this work, we extend this this framework and we reduce the hidden multiple shift problem to a new classical problem, which is called the learning from subset problem. So the learning from subset problem can also be thought of as a problem where you have partial information about the linear equations. So let me try to define it rigorously. So I have to define first the sampling distribution from which you get samples. So an AL distribution on ZQN for a linear function L is a distribution such that the probability of sampling U is a function only of LU. And it's non-zero if and only if LU belongs to A. So if you draw a sample from an AL distribution, you know that that LU belongs to a certain finite set. Like LU can be 1, 2, 3, or 4, let's say. That would be the analogy. And the learning from subset problem is given independent samples from the AL distribution with the size of A equal to D to recover a constant multiple of this linear function. So that's the so at a high level it's for each linear equation you're given a fixed set of values that it might take. Like you don't know the exact value of LU, but you know that it lies in a finite set A. So now I'm going to state the main results and the main steps used to obtain these results. So the main result is, of course, that for a prime Q, there is a quantum algorithm for HMS QMR, which has this complexity, and there are two main steps for obtaining this result. So the first is a quantum polynomial time reduction from the hidden multiple shift problem to the learning from subset problem. And the reduction is such that the linear function is exactly the shift. Like if you know L, LU is equal to U dot S. So the first step is reduction to LFS, and the second step is an algorithm for LFS. So the second step is an algorithm for LFS with sample complexity n plus d to the power d and running time polynomial in this and log Q. So I'll explain why this log Q comes up. So in this talk, I will first discuss the second result, the algorithm for LFS, and then come to the polynomial time reduction. So both of these, so we'll first talk about the learning from subset algorithm. So there's an algorithm with sample complexity n plus d to the d and running time polynomial in the sample complexity and log q. So each sample is n tuple and of vectors from zq. So it has so the input size is n log q. So polynomial time algorithm should be polynomial in n and log q. So if d is a constant, then this running time one can see that it really gives you a polynomial time algorithm. So so let me compare to previous work. So we recovered the previous algorithms by Friedl and others in 2004 and by Vanios in 2008 for the learning from disjunctions, which is LFS Q(n)(q)-1 with running time poly n plus q to the q. So this is just the case when d is equal to q minus 1. And the algorithm we give here is asymptotically faster than the previous algorithms whenever d is smaller than q, whenever d is OQ. So, okay, so now I'm going to describe the idea for this LFS algorithm. So the first observation is that there is a degree d polynomial which vanishes for all x in the support of an AL distribution. So remember that in AL distribution, Lx can take exactly d different values. So if you take the product of Lx minus a for all the possible values it can take, then this is a polynomial of degree d, and it vanishes for all x in the support of the AL distribution. And further, all the degree d polynomials that vanish on the given samples, like if we are given samples u1, u2 through uk, then all the degree d sample polynomials that vanish on these can be computed by solving a linear system over fq of size n plus d to the d. So the coefficients of the polynomials would be the unknowns, and one just linearizes and writes out linear equations, one for each sample. And then this very large linear system would give you all the polynomials which vanish on your samples. So the naive hope would be that if one takes enough samples, the only polynomial which vanishes would be this polynomial FALX, which I defined above. But what one shows is a bit different. So let's see what we can prove. So we can prove that for P, so let P in A be the point for which the probability of LU being equal to P is maximal. So the theorem that we prove is that with constant probability, every polynomial that vanishes on M equal to poly n plus t to the d IID samples from an AL distribution is divisible by Lx minus alpha p. And this is good enough to obtain an algorithm because there is a algorithm due to Kaltoffen to factorize polynomials over a finite field and recover the linear factors. So one first would solve the linear system to get the polynomial and then use this factorization algorithm. And one of the factors would be guaranteed to be Lx minus alpha p. And clearly one can recover Lx once we have this factor. So again the theorem. So let ui be IID samples from an AL distribution with a equal to d and m is polynomial n plus t to the d. Then with high probability, with constant probability, with probability half, all the degree d polynomials which vanish on all these samples are divisible by Lx minus alpha p. And given the theorem, the algorithm is to find the polynomial by solving a large linear system, then to factorize this polynomial using Kaltoffen's algorithm and find L from one of the linear factors. So I'm now trying to sketch the proof of this theorem. So at a high level, the proof is based on a variant of the Schwarz-Zippel lemma and a dimension argument. So let me begin with the variant of the Schwarz-Zippel lemma. So let Gx be a polynomial of degree d that is not divisible by Lx minus alpha. And let V alpha be the set of all the points where Lu takes the value alpha. Then if U is sampled uniformly from V alpha, if U is sampled uniformly from all the points where Lu is equal to alpha, then the probability Gu equal to 0 is less than d by q. So this is a variant of the Schwarz-Zippel lemma. The Schwarz-Zippel lemma in the normal case, would sample points uniformly from the field and would get a bound d over q if the polynomial is non-zero. And one can get this variant by first doing a division algorithm. So we know that gx is not divisible by lx minus alpha, so we write it as a quotient and a remainder. The remainder is non-zero, and to the remainder you apply the normal Schwarzschild lemma to get this statement. So this statement will be the main technical tool which will drive the argument. So remember, we are studying all the polynomials which vanish on the samples ui, which are IID from the AL distribution. So let's define pk to be the space of the degree d polynomials which vanish on the first k samples. And let p prime be the subspace of all the degree d polynomials which are divisible by lu minus alpha p. So the theorem that we want to prove is that for large enough k, pk should be a subset of pu prime, of p prime. So, okay, so the first observation is that that p naught has dimension n plus d to the d. Like p naught is the set of all the degree d polynomials. And then pk plus 1 is strictly a subset of pk. So these form a chain of descending subspaces. And the goal is to show that eventually they will all fall within p prime. So the way to do it is under the assumption that pk is not in p prime, that if pk is not yet in p prime, then we show that pk plus 1 is a strict subset of pk with probability at least 1 by d plus 1. So if it is the case that pk is not in p prime, then the dimension is going to decrease with some small probability. And the dimension can't keep on decreasing indefinitely because it starts with n plus d over d binomial. And so eventually we would come to a stage where pk has to be in p prime. So let's see how one proves this claim. Like that's the main idea of the proof, and then so the implication pk not in p prime means that there is a polynomial gx such that gui is equal to 0 for all I in k, like it vanishes for all the first k samples, and gx does not have lx minus alpha p as a factor. So the probability that pk plus 1 is equal to pk is at most the probability that guk plus 1 is equal to 0. And it's this probability that we can bound with the Schwarzschild lemma. So to bound the probability that guk plus 1 equal to 0, let's condition on luk plus 1 equal to alpha p and expand this probability out. So alpha p, remember, was the element which occurred with the maximal probability in the AL distribution. So the probability pi of LUK plus 1 being alpha p is at least 1 over d. So the probability GUK plus 1 equal to 0 conditioned on LUK plus 1 equal to alpha p is at most 1 minus pi plus pi times d by q, where here I applied the Schwarzschild lemma. And then one can calculate as d is less than q minus 1, it follows that this probability is less than 1 by d plus 1. So it's a simple calculation, but it's omitted here. So the upshot is that if pk is not in p prime, then pk plus 1 is like the dimension decreases with some constant, some probability, 1 by d plus 1. So beyond this claim, one needs that the dimension decreases with. So now we split the samples into blocks of d square log n samples. So n is the dimension of p naught, which was log n plus d over d. And for each block, one can argue that the dimension decreases with constant probability. And then applying a union bound, we get that for the whole sequence. So for d square log n multiplied by n, the dimension would go down to 0 with high probability if pk is not in p prime. So I try to convey a high level a sketch of this proof, and it's actually a quite short proof. Like if you're interested, you're encouraged to look at the paper. So now I move on to the second idea, which is this quantum polynomial time Turing reduction from HMS to LFS. So together with the previous result, it implies the first polynomial time algorithm for HMS Q and R for Q equal to poly n and for constant Q minus R. So the previous algorithms would have worked for constant Q and also a polynomial time algorithm for HMS Q1 and large R was given by Childs and Van Dam in 2007. But so this is so the dimension here is 1 of so. Okay, so now let's see how to do this reduction. So we use the standard pre-processing. So I showed you what the quantum states were in the first slide. So for the hidden multiple shift problems, one obtains quantum states of the form 1 by square root r a plus HAS times h. So the standard pre-processing on this is to apply a Fourier transform on the first register and do a measurement. So let's say we measured the state, we measured u for the first register after doing the Fourier transform. So then we would obtain a sample u and mu t, where t is the inner product between u and s, and mu t is the state. It's 1 by square root r omega HTH, where omega is the qth root of unity. So again, this is standard pre-processing. This is well known to from previous works on these problems. So let's look at the mu t's. So the mu t's span an r-dimensional subspace. So each mu t from the equation above, you can see that it's a sum over h in capital H. So and h has size r. So they span a r-dimensional subspace. So define a hyperplane V, which is the span of the first, so it's a span of mu naught, mu1 up to mu r minus 2. So there are r minus 1 of them, and shortly I'll show that they're linearly independent, so it's really a hyperplane. So the idea is to measure mu t in the VV perp basis. So measure it along the hyperplane and its complement, and retain only if the measurement outcome is in V perp. And the claim is that if we do this measurement, we are sampling from an AL distribution, like we retain, okay, so if U is retained, then we know that LU, which is U dot S, belongs to R minus 1, R through Q minus 1. And the probability of retaining U depends only on LU, because it depends only on mu T. And so now the U's that are being retained are ID samples from an AL distribution with A is equal to Q minus R plus 1. And now the LFS algorithm can be used to solve this problem. So in order to make this approach work, one needs to show that we are not discarding all the samples. So we need to prove a bound on what's the probability that the samples are retained. So the way to we show this bound is to note that the matrix with the columns uj, where uj's muj's, where the muj's were defined here, is a van der Waals matrix, and so its determinant is well known and it can be lower bounded. So if one calculates the determinants and use the Cramer's rule to solve the linear system, then one can see that for r minus 1, the projection onto the span of onto V perp is at least q to the q minus r squared times q over r to the r. Okay. So because of this nice algebraic property that this is a van der Waals matrix, one can actually bound the probability of discarding the. And of course, there's a question of how to implement this VV perp measurement. So there can be a specialized procedure for it, but also it's only on log q qubits, so it can be implemented generically using the Solovay-Kitaev theorem with cost only q squared. So okay, so I showed you how to solve the LFS problem and how to reduce the HMS to the LFS, and combined these to give an algorithm for HMS Q and R with running time n plus q to the q minus r squared. So I'll conclude with one open question, which is to find an algorithm for HMS Q and R that is polynomial in n and log q. So that's the most immediate open problem that one could hope to extend following the ideas in this work. Okay, so thanks.
Plenty of time for questions. further questions, let's thank Anupam for his talk.